Hello everyone, and welcome back to this new video of the Agentic AI series. Today we are talking about a new component of the core components, which is one of the most misunderstood components, but yet one of the most important components of Agentic AI systems, which is the memory. Memory not as chat history, memory not as vector databases, but memory as an architectural subsystem of agentic AI. If we remove memory from an agent, what do we get? We get just a stateless function, and a stateless function cannot learn, cannot adapt, and cannot build continuity across time, which is all of them are enabled by memory. We know agency requires continuity, and continuity requires memory. And in that sense, memory is enabling adaptation, learning, identity, and behavioral stability. So, memory is not the storage. We are talking here about memory as a controlled influence over the behavior across time. Here in this example, we see on the left side a stateless agent. Let's name it agent for the moment. And on the diagram, we see the user request goes to the agent with a goal, and the agent will produce a result. But when a new session comes in, we see that the agent restarts from scratch as if it has no history because it has no memory here. And it reproduces another result as which might be not related to the first one or probably the same one without learning from that experience. And here, if you see, we have added the question mark and exclamation mark in the agent box because I'm not sure that we can call it an agent because it doesn't have agency as it doesn't have memory here. And that's a crucial distinction here. While on the right side, we see a stateful agent where the user sent a goal to the agent and the agent produces a result, but as well it writes updates in the memory. And when a new session comes in, the user sends a request with a goal, and the agent retrieves the relevant memory from the past experiences, from other memory sources that it has, and it produces another results. And again, it tries updates to the memory. And here we can see the distinction actually between the, let's say, the two types of agents, one with memory, without memory, and another one with memory, and how memory enables learning over time, enables continuity, and affects actually the behavior. And so we can see behavioral change over time from that agent. So when we say memory, what do we mean actually by memory? Let's start in the beginning with this memory hierarchy. In agentic systems, memory naturally splits into layers, and the most famous two layers are the short-term memory and the long-term memory. In the short-term memory, we mean that we have the context window, prompt, chat history. It is the actual active computational workspace for of the model. While the long-term memory, it is a persistent storage. It lives outside the model. It doesn't resides within the model itself. And in the long-term memory, we typically distinguish between two types of memory here, which are on the right side on this slide: the semantic memory, which is the knowledge that is generally true, and that includes policies, general facts, rules, and so on. And the episodic memory, which is the experience that the agent has gone through, uh, from failures, successes, lesson learned, and so on. And here, the critical insight actually, only one of these memories or memory layers actually thinks or participates in the thinking process, which is a short-term memory. Everything else exists outside the model, and its role only to decide actually what goes and what enters the short-term memory, which afterwards will participate in the thinking and reasoning process. Short-term memory. Um, let's start with that. In general, the short-term memory, as we said in the previously, it is the context window, and it has four critical properties. First, it is bounded. Second, it is expensive. Third, it is order sensitive. And fourth, it has high casual impact, actually. So every token in the prompt shifts the probability distribution of the next token to be generated, which means a relevant memory is not neutral, actually. It is actively harmful. So, and here we come to a common mistake in agent systems, which is when we store everything and we retrieve top K and append it to the prompt, hoping that the agent or the model will figure it out. And this will lead actually to degradation over time. And this is something we call sometimes memory poisoning or context poisoning. And because the more the system remembers, the worse it becomes. And here the system remember and means in the short-term memory, while good agents actually they store more, they have more knowledge, but they think with less. They don't use a lot of information to think with, but the short-term memory is very kind of distilled. It is the essence of the memory that is relevant at this very specific moment for the agent. So the short-term memory should not reflect what the agent knows, but rather it should reflect what the agent needs right now in this very specific moment, which is very crucial for the agent to perform the current task under the current circumstances. Now we move to the semantic memory, which is one part of the long-term memory. In general, semantic memory stores knowledge that includes policies, documentations, principles, rules, constraints, etc. And it answers the question, what is generally true as a matter of fact? In practice, semantic memory is usually implemented with embeddings and vector search. So we chunk the documents, we embed them, and then we retrieve the most similar chunks to be used in the short-term memory. But here, another crucial point, similarity is not enough. But what we say here, relevance is the most important keyword in this part. And relevance is not just semantic similarity. It is semantic similarity conditioned on agent state. So based on the agent state and the semantic similarity together, we get the relevance. And we will see that in the implementation, how semantic memory can be distilled according to the agent state and so on. So semantic memory in general is stable, and it should not drift every time the agent has a local failure or has gone through an experience, success, or summarize a lesson learned and whatever. So it's in general, it should be stable over time. It doesn't change unless the general facts have changed, but otherwise it should remain stable because it represents the knowledge of the world, not the memory of the mistakes or the memory of the past experiences of the agent itself. On the other hand, episodic memory is different from the semantic one because it stores the experiences and the past history of the agent. And typically, we usually store in the episodic memory the goal, the context, the actions taken, the outcome, the lesson learned, and so on. And the episodic memory answers the question, what happened to me before? So the agent is remembering actually what happened in the past, in his past experiences. In Generative agent research, this looks like memory streams and reflections, unlike in reinforcement learning when this looks like experience replay. Episodic memory is how the agent improves uh, without retraining weights, actually, unlike reinforcement learning. So instead of a gradient descent, they perform text based consolidation. So the process goes as the agent, for example, fails, then summarizes the experience, stores the lesson learned, and then retrieves it later for another episode of experiences where they can learn from that past experience. So this is a mechanism how that allows the agent behavior to change over time in a way that simulating the human learning from past experiences. Now we arrive to the core problem in memory systems, which is the relevance. Most memory failures are relevance failures. They are not that we forgot something, but they are probably we loaded something wrong into the short-term memory, or we loaded too much, or probably we loaded something correct, right, but at the wrong time. So mainly, these are the memory failures. So we this concludes to us that relevance depends on the current state of the agent. So it's not about the knowledge itself or the parts of the memory that is stored, but it depends on what is needed in this right moment for the agent to perform its task. For example, in planning mode, semantic and episodic memory are useful. Both are relevant to the agent to perform its task. So we need to distill from both of them the relevant chunks, as we said, to be brought to the short-term memory so the model can reason and think on them. While in execution mode, long-term memory has no role to play with that because in and probably it can be dangerous because it might lead to hallucination with the execution, especially when we do tool use and so on and so forth. So this is where we don't use actually long-term memory. But on the other hand, in reflection mode, episodic memory is the only one that is dominant. Actually, semantic memory has no play to role because in reflection mode we need to reflect on past experiences, the current experience, and learn from it and reflect on that and update the episodic memory accordingly. So memory selection should be state aware, and here we know that similarity search is not enough by itself, but we must gate the memory through the life cycle by life cycle stage, by the agent status, and so on. And as we see on the slide, we say memory is a function or relevance is a function of memory, state, and task. So they are kind of correlated to each other. And relevance function in general and this distillation from the long-term memory to the short-term memory goes under what we call context engineering. So we have in the pipeline, we have the long-term memory store, and from it we retrieve our candidates that are potentially relevant, and then we apply the state filter. So we select less candidates here, and then we cap by token budget according to the resources that we have at the current moment, and then we assemble the short-term context that we provide to the model to start reasoning with and thinking with. So as we see here, memories must pass through a gate starting from the state filter, token budget, and etc. and so on. So memory is not only the retrieval; it's about orchestrating all of these elements together, from retrieval, filtering, capping, and assembling the short-term context with the current state itself. So this is how we see the context engineering in a brief, but we can go deeper in this in a separate video. And to complete the memory life cycle, let's say, or cycle, after we had the context assembled and the model reasoned and thought with the short-term memory, with the context, and it performs the actions. So now it's time to reflect on what happened. And from there, we have the experience, and the model or the agent will summarize that experience and then right back to from the short-term memory to the long-term memory here, to the episodic memory, the lesson learned, that will be retrieved later at a later stage in another session. That will how we see the memory evolving, and it influences the behavior over time. So, in a nutshell, uh, memory system in Agentic AI has two main types: long-term memory, which is a reservoir that includes semantic memory and episodic memory, and the short-term memory is the workspace where the agent functions actually, and relevance, as we said, controls the influence, and reflections updates the memory with new experiences. Um, Finally, memory is not accumulation, it is control. This is important to notice here. It's the control over behavior, over across time, and it is that orchestration between what we store, what we remember, what we retrieve, what we use at every single moment of the life cycle of the agent, and so on. So that's that whole orchestration is the memory, not only the stores themselves, not only the accumulated knowledge or experiences, and so on and so forth. So this is really crucial to distinguish in memory systems. Now, we're done with this first part of the memory systems in Agentic AI. We will move next to the implementation of what we have discussed here, short-term memory, long-term memory, and so on, in a notebook that is runnable in Google Colab. I always come back to this slide to show where we stand on our roadmap. Today we are talking about memory system as part of the core components. Next video will be about tool use and API, and we will continue the journey until we cover all the components of the Agentic AI engineering. Don't go far. We'll continue in the next part with the implementation shortly. See you there.